Once we have a question we want to answer, we have to decide how we are going to research it. A single research project is often called a study, and studies can have different structures, called designs. Different research designs are appropriate for different question types because they allow us to draw different kinds of conclusions. Descriptive designs can answer descriptive questions. A study with a descriptive design will provide a rich picture of what something is like. In a descriptive design, all the researcher does is record what exists, almost like trying to take a picture. The data is descriptive and illustrative. The researchers might give basic figures, such as 4 people did X or 60% of people said Y, but there will be no statistical analysis, and usually the emphasis is on verbal description and quotation. The purpose is to present something vividly, rather than to investigate a very specific pattern. Correlational designs can answer relational questions. Like in a descriptive design, the researcher is recording information that already exists in the world. Instead of trying to paint a holistic picture, however, a correlational design measures a set of specific factors in order to see how they relate to one another. The data is always quantified in some way, and statistical analysis is used to determine whether relationships exist. For example, we know that people differ in height and that people differ in how much they like dogs. We could measure how tall people are and how much they like dogs, on a scale from 1 to 10, for instance, and then we would use statistics to determine whether there is a pattern here. Maybe the taller you are, the more you like dogs. You've probably heard the phrase, correlation does not imply causation. Why is it that correlational designs don't produce evidence of causal relationships? Well, correlational designs measure differences at a single point in time, so we can't tell what came first. This is the problem of reverse causality. If A and B are correlated, that could be because A causes B, but it could also be because B causes A, and we will have no way to tell. There are some ways to get around this, like for instance by taking multiple measurements over time, but there's another problem with correlational designs. Let's say we find out that places with well-landscaped lawns also tend to have high-achieving schools. So landscaping and school achievement are correlated. Is there likely to be a causal relationship here? No. Instead, it's likely that a third variable, like community wealth, causes both. This is called the third variable problem, or the problem of confounding variables. Although it's possible to rule out some confounds by concluding those variables in our analysis, it's impossible to know whether there are other confounding variables we might have missed. So correlation is like the first step in determining how things are related. Variables that are correlated may or may not also have a causal relationship. But variables that are not correlated at all almost certainly do not have a causal relationship. Experimental designs can answer causal questions. Unlike descriptive and correlational designs, the researcher doesn't simply record. In an experiment, the researcher interferes by manipulating what people experience in order to see what happens. Remember that factors have a causal relationship if one factor directly changes the other. In an experimental design, the factors you suspect cause change are the independent variables, and the factors you suspect get changed are the dependent variables. The researcher creates different versions or conditions of the independent variables for people to experience, and then they look to see whether the dependent variables differ based on what condition people experienced. The data from measuring the dependent variables is always quantified in some way, and statistical analysis is used to determine any differences between the conditions and whether they're meaningful. Why do experimental designs produce evidence of cause? Well, let's say that I want to know whether what you eat for breakfast has any impact on how well you can take a test. Now, there are clearly many factors that influence how well you do on a test. Test performance naturally varies. If I give a test to our class, there will be an average level of performance, with some students doing better than that and some doing worse. If I randomly split the class in half, randomly assign each student to either group 1 or group 2, all of the variation that existed in the whole class will get evenly split, and I'll end up with two groups whose average test performance is about the same. This random assignment is the key to experimental design. Now I can take these two equal groups and have one group eat eggs for breakfast and the other eat waffles for breakfast. Breakfast food is my independent variable, and there are two conditions: eggs or waffles. Then I could give the whole class the same test. Score on that test is my dependent variable. Finally, I see whether there was any difference in test score between the group who ate eggs and the group who ate waffles. Although there will be variation within each group, both groups should have had about the same average performance because of the random assignment. If the two groups have different averages after eating the breakfast foods I assigned, what could have caused the difference? Well, if the two groups are the same in every other way except what they ate for breakfast, it must have been the foods that caused the change. There can be a lot of similarities between studies using correlational designs and studies using experimental designs. In fact, data from both types of designs can be analyzed using a statistical value called the correlation coefficient. The correlation coefficient, represented by R, indicates how well you can predict one variable using another. It's a number between -1 and +1 that describes the strength and direction of a relationship. Positive values means that as one variable increases, the other variable also increases. If you plot the data, they slope upwards, like they do on the top here. Negative values mean that as one variable increases, the other variable decreases. The data slopes downwards. Values closer to positive or -1 indicate a strong relationship. You can predict one variable very well using the other, and the data will start to form a line the closer you get to 1, positive or negative. Smaller values indicate a weak relationship. When the coefficient is very close to 0, there's no identifiable relationship between the variables. The data will be all spread out, like it is on the two graphs on the right. When we say that correlation doesn't imply causation, we are talking specifically about correlational designs, not about correlation as a statistical tool. Data from experimental designs can be analyzed using correlations, and data from correlational designs can be analyzed with more complex techniques. The ability to claim causality comes from the design, not from how the results are analyzed. For example, let's say we're interested in finding out whether playing violent video games makes kids more aggressive. We could study this using a correlational design or an experimental design. In a study with a correlational design, we would follow 100 kids for a week, measuring how many hours they spend playing violent video games. Then we would measure how many acts of aggression each kid performs, maybe by watching them during recess or something. Then we would take the data from those two measurements and calculate the correlation coefficient. In a study with an experimental design, we would take 100 kids, and instead of simply recording how many hours of games they play, we would randomly assign each kid to play games for a certain number of hours for a week. So we'd have some kids playing no games and some kids playing a lot. Then the rest of the procedure could be exactly the same as in the correlational design. We would measure how aggressive the kids are and then calculate the correlation coefficient. In both cases, our result would be a measure of correlation, -0.3 or +0.7, something like that. But if we used the experimental design, we would have evidence that that correlation is due to the effect of video games on aggression. If we use the correlational design, we would only know that they're correlated and not why they're correlated. Maybe some third factor causes both aggression and violent game playing. Importantly, it's not that we can't ever draw causal conclusions based on correlational evidence. We just require much, much more of it before we can do so. Take something like the idea that smoking causes lung cancer. No one has ever randomly assigned some people to smoke for 20 years and some people not, and let's see who gets lung cancer. Instead, we have a ton of data from correlational studies, numerous studies conducted over time, paired with experimental data from animals, and that makes us feel comfortable asserting that smoking causes lung cancer. Correlational data is suggestive, but until the correlational evidence is truly overwhelming, we need to be skeptical of causal claims.